When the electron, or when n is equal to 1, what we say, the language we use, is that we say that the hydrogen atom, or we say that the electron, or the hydrogen atom, is in the ground state. We call this the ground state because this is the lowest energy state, right? It's got the most negative energy. It's the lowest energy state. We call n equal 1 the ground state of the hydrogen atom, or the ground state for the electron. We use those terms of the electron or the hydrogen atom interchangeably. Now, what's the significance of this binding energy? And this is important. The significance is that the binding energy is minus the ionization energy for the hydrogen atom. Because if I put the energy, this energy in from here to there into the system, well then I will be ripping off the electron and I'll have a free electron, right? So the ionization energy is minus the value of this binding energy. The ionization energy is always positive. The binding energy, the way we're going to treat this, the binding energy is going to be negative because the electron is bound, right? And then the separated limit, the electron far away from the nucleus, well, that energy is 0, all right? So the binding energy is minus the ionization energy, or conversely, the ionization energy is minus the binding energy. That is the physical significance of these binding energies, right? And when we talk about an ionization energy for an atom, we are typically talking about the ionization energy when the atom is in the ground state. This is the ionization energy we're talking about. All right? All right. But we also said that the binding energy of the electron can be this much, meaning it's in the n equal 2 state. Right? That can be possible also. Not at the same time as it's in the n equal 1 state, but you can have a hydrogen atom in a state which is the n equal 2 state. What that means is that the electron is bound by less energy. When that's the case, we talk about the hydrogen atom being in the first excited state. This is the ground, this is the first excited state, but n is equal to 2. All right? In that case, the electron is not as strongly bound because it's going to require less energy to rip that electron off, right? The binding energy in n equal 2 is just the ionization energy, or the binding energy in n equal 2 is minus the ionization energy if you have the ionization from the, if you have a hydrogen atom in the first excited state. All right? Makes sense to you? Yeah? Okay. So we can have atoms in this state too. Then the ionization energy is less. It takes less energy to pull the electron off. Yes, please.
On a question, does the ionization energy only apply to those negative binding energies or to all of them?
In everything that we're going to deal with, we're going to have binding energies that are negative. Okay? So let's do that. You can of course have a binding energy that's positive, but the problem is that isn't a stable situation, right? Right. Okay. Okay. Good. Other questions?
Is ionization energy related at all to the work function?
Yes. Okay. When we're dealing with a solid, we talk about a work function as opposed to an ionization energy. When we're dealing with an atom or a molecule, we talk about an ionization energy as opposed to the work function. It's really the same thing, okay? We just, historically, there's a reason for calling the ionization energy off of a solid the work function, okay? I just wanted to point out again, right here, is that when n is equal to infinity, the binding energy is 0. That's the ionization limit, all right? That's when the electron is no longer bound to the nucleus. this solution to the Schrodinger equation for the hydrogen atom, this solution works. It predicts the energy levels, the allowed energy levels for any one electron atom. All right? What do I mean by one electron atom? Well, helium plus is a one electron atom, right? Because helium usually has 2 electrons, but if you take one away, you have only 1 electron left, and so this helium plus ion, that's a 1 electron atom, or if you want to say it more precisely, 1 electron ion. All right? Or lithium double plus, hey, that's a 1 electron atom or a 1 electron ion. Because lithium usually has 3 electrons, but if you take 2 away and you only have 1 left, hey, that's a 1 electron atom. Uranium plus 91 is a 1 electron atom, okay? Because you took 92 of them away, 1's left, that's a 1 electron atom or an ion. And the bottom line is that this expression for the energy levels predicts all of the binding energies for 1 electron atoms, as long as you remember to put in the z squared up here. Okay, for a hydrogen atom, that's of course z equal 1, so we just have minus r sub h over n squared. But for these other 1 electron atoms, you have to have the z in there, the charge on the nucleus. Why? Well, because that z comes from the potential energy of interaction. The Coulomb potential energy of interaction is the charge on the electron times z times e, the charge on the nucleus. That's where the z comes from. All right? That's important.